So I do want to thank the organizers of this workshop for the opportunity to share some of our thoughts on the statistical methods, specifically the approaches to causal inference that can be valuable in the accountability context. And I'll use these slides as somewhat of a jumping off point to start the discussion, but I won't go through all of them. I think what I'll try and do is tailor the discussion a little bit more to what's already been talked about. It's already been talked about today. And I should say, before we get started, that the funding that has provided the support for a lot of our time spent thinking about these types of issues is from HEI. So I wanted to start with, I suppose, a little bit of a thought experiment for everybody. So I want us to try and picture two different analyses, both of which have been represented, I think, in the discussions today. So the first type of analysis that I'd like us to think about for a minute is the analysis, let's say one like Arden was just speaking about, some of the life expectancy analyses that have played a very important role in this area, where we have spatial and temporal variability in, let's say, TM and whatever health measure we're interested in, life expectancy. And let's say we had perfect information. Anything that you could possibly conceive of as a confounder of this relationship was measured, and it was measured perfectly. Let's say, despite Arden's humble comments about his modeling strategies, let's say he was spot on, he directly got his regression model exactly right, or whatever model, exactly right. And we had an estimate of what we frequently refer to as the health effect. Everybody with me so far? And we know this is actually the health effect. This is not measurement error. There's no confounding bias here. There's no selection bias. Nothing like that. This is the health effect. We know when when PM changes by this much, we expect a change in life expectancy by that much. So that's one analysis. And think about that as a health effect. Now, to contrast that, another type of analysis that we've talked about today is that where we look at a specific intervention. The EPA, let's say, has a particular regulatory decision that they make at some point in time, the prostate air pollution rule, something along those lines. And we have a different analysis, and in that analysis, we estimate the causal effect of that intervention strategy on PM, and we estimate the causal effect of that intervention strategy on health. And we say that same thing, any confounder, anything that we can possibly think of, we measured it, we have it perfectly. Now, what I'd like to try and do is really try, and even if I sound like a broken record, hammer home the difference between these two types of analyses. I hope everybody can see how the health effect, as interpreted by a coefficient in some model of a trend over time, delivers different information than saying what is the health effect of making this decision or conducting this intervention. And I think to promote accountability moving forward and to conduct this type of research, it is helpful to be exactly clear about what we want. What exactly is the question we're trying to answer? Are we trying our best to characterize the relationship between pollution and health, or are we trying to evaluate the consequences of a specific action that the EPA has taken or is considering taking? And I don't mean to place any more value on one of those approaches over the other, but just to draw a distinction between them, because what I'd like to talk about for the next few minutes is more the methods, the difference, the methods, statistical methods we need to think about for the latter type of question. The EPA as a regulatory agency or some other regulatory agency can make certain decisions, they can take certain actions. What are the effects of those actions? And I think there are different demands to those, to conducting those types of analyses. So in the white paper, in some ways the thesis of this white paper was to draw a distinction between what is sometimes referred to as the quote-unquote classical paradigm for causal inference and a more modern potential outcomes paradigm for causal inference. So the classical paradigm is the one that I would say has served the field well for a long time, where, and this is very broad obviously, we would first estimate some association between pollution and health. This is often some coefficient in some sort of regression model, which we refer to as the health effect. And after we estimate that association, we then go through the whole rigmarole of deciding how willing we are to believe this is actually a causal relationship. And that's, we have toxicology studies, we can try and reproduce this effect estimate in other populations and so forth. We can think of every confounder under the sun that we have or a proxy for that confounder to adjust for. But the basic idea is once we estimate some association, our judgment about causality is thought of as on a continuum. Oftentimes, a more rigorously conducted analysis is one we are more likely to value as a causal analysis. But in this framework, there's no clear definition of cause and effect. There are risk associations that are estimated, and we use our scientific knowledge and try and decide the extent to which we believe those are causal associations. Now, in contrast, in a lot of fields of epidemiology, statistics, econometrics, political science, implementation science, there is a more recent framework for causal inference rooted in this notion of a potential outcome. But the key idea in this framework is that causal effects are specifically and explicitly defined as consequences of actions. And this is something that I think is particularly relevant to accountability assessment. We have interventions, or we're planning interventions, and we need to know how to evaluate the causal effect of these interventions. And so what unfolds in the white paper is essentially a three-step process. We can frame an accountability assessment, the assessment of some intervention, as if it were a hypothetical experiment. So this is related to the notion of the natural experiment. It's related to notions of quasi-experimental methods. But I think this, and then, so we frame this problem as evaluation of some hypothetical experiment. And really where a lot of the action is here in terms of being able to develop methods to actually do this comes to identifying a relevant control population to use as a comparison arm in our hypothetical experiment. And after we formalize these first two steps, then we can estimate causal effects. I'll say a few words about them, and I'll try towards things that I think we need to keep in mind as we think about doing this type of analysis in the future. Skip this. So the basic idea with framing an accountability assessment as a hypothetical experiment is as follows. When we have some intervention that's been, let's say retrospectively, it's been implemented. So for example, the non-attainment designations for PM10, which first started in the early 1990s, we need to define some control condition and pretend this were a trial, an experiment that we ran where we assigned some areas to be designated as non-attainment and in some areas, let's say, for a control arm to not be designated as non-attainment, where let's say pretend the EPA didn't do anything about PM10 at this time. And the idea is that if we can be clear and explicit about what the intervention and control arms are of this hypothetical experiment, we can be similarly clear and explicit about what would have potentially happened to pollution and health under each of these scenarios. Now, we don't get to observe all of this, but we can be explicit about this. And if we can define the potential pollution and health outcomes under the intervention scenario, which we would often observe, and we can explicitly define what pollution and health would have been had, in this case, the EPA done nothing, let's say, in the control population, then we can explicitly define causal effects as comparisons between what happened and what would have happened under some alternative scenario. This is the idea. And we can similarly define these causal effects for health. But a couple of key points that I want to make here. One is that this setup has nothing to do with any particular statistical model. There's no beta. We haven't decided to do time series. We haven't decided to do regression. We haven't decided to do a hierarchical model. We've made no decisions about statistical modeling. We're just formalizing the question at this point. And we're being completely explicit. Once we define what the hypothetical intervention and control arms are, we have defined a causal effect. This is the question. What was the causal effect of this intervention versus had the EPA done this other action, this control action? And so in terms of this type of analysis, of course, there are several things to keep in mind. One of which is relevant control condition. Is what I put on this slide is the EPA designated areas as non-attainment for PM10. What's the relevant control condition? The EPA doing nothing? The EPA doing something else? But as long as we know that defining this hypothetical intervention is going to define the causal effect that we're going to estimate at the end of the day, we need to make sure we're defining a causal effect that's actually of interest from a policy standpoint. So that's one point. The other point that we've bumped up against in some of our work is that we need specific data on the quote-unquote the cause. And this might seem somewhat obvious, but it's not always obvious. So in our work in estimating causal effects of the non-attainment designations, we've gone to the Green Book, and you can see which areas are designated as non-attainment. And we can define and estimate the causal effect of a non-attainment designation. Now, we also know that different areas do, different states do all kinds of different things if they're designated as non-attainment. Some areas don't do anything if they're designated as non-attainment. But we don't have data on those actions. And so there is sometimes a disconnect between evaluating the causal effects of a particular decision, in this case a non-attainment designation, and evaluating the causal effects of some actual specific action, spraying windblown dust in California. And that's important to keep in mind as we move forward in thinking about future accountability studies. So the other place where the real action is in being able to do this has to do in identifying the relevant control population, the control group of this hypothetical experiment. So the basic idea is if we have a control group that is comparable to the intervention group, and we can use observed data on this control group to predict what would have happened absent the intervention. So we have certain areas of the country that are subject to some regulation and certain areas that are not subject to that regulation. And the idea is that if those areas that are not subject to the regulation can be made to resemble those areas that were subject to the regulation, we can look in those control areas to learn about what would have happened without the intervention because they didn't experience it. So the moral of the story where the rubber hits the road on this type of analysis is confounding, as we know. But I did want to say something about confounding in this case. So we're used to thinking about confounders as things that are associated with exposure and outcome. So something that's associated with exposure to air pollution and associated with some health outcome. In this case, the notion of a confounder is slightly different. The exposure in this case is the intervention. And the outcomes are pollution outcomes, health outcomes. So when we talk about a confounder in this type of analysis, we're talking about a factor that differs between intervention and control areas. So somebody earlier, where I said population density. As an example, so let's say population density was equally distributed in attainment and non-attainment areas in the U.S. I don't think that's actually true, but pretend that it were true. We have non-attainment areas, we have attainment areas. Population density tends to be the same on average in these different groups of areas. Population density is not a confounder. Even though we know population density is likely associated with exposure to air pollution, we know population density is likely associated with any number of health outcomes. The key idea of a confounder is does this factor differ between whichever areas we're calling the intervention areas and whichever areas we're calling the control areas. So I think it's a little bit different than what maybe we're used to thinking about in the classical paradigm of causal inference. In terms of considerations in moving forward, I'll really only draw out two of them. The first one on this list is any conclusion that we are going to make about this type of causal inference is going to rely on data on both the intervention areas and the control areas. So focusing data collection efforts, for example, only on areas where the intervention is implemented is not going to get us anywhere in this framework. We need anything we have collected on people or on areas subject to the intervention, we need that information also collected on the control population. So that's one point I wanted to make. The last point I wanted to make is the last one. The whole idea of we can think of confounding adjustment in this context as taking these control areas and adjusting for certain factors to make these control areas look like the intervention area. So we can conceive of adjusting for confounding in this sense. There are some areas for which we will never be successful in doing that. So the example I gave in the white paper is Los Angeles County. There are some monitor locations in Los Angeles County which was designated as non-attainment for PM10. And there are parts of Los Angeles that don't look anything like any other place in the country in terms of their demographic makeup, in terms of their air pollution, ambient air pollution levels. And in some cases, there will be no level of compounding adjustment that can find us a relevant control population to compare to some place in central Los Angeles. And in that case, and this is something that might not sit well, it is sometimes, I would say, required to throw some of these observations out of this type of causal analysis, which, as a statistician, you think, how many people live in that part of Los Angeles? It pains my heart to throw that type of thing out of an analysis. But the point is, when some areas are so different on the basis of anything that we're calling confounders, we cannot make a call on the data, which is that we don't typically like to do. So that's the point, and we can talk about that a little bit more if folks are interested, but it's the point I wanted to make. So in terms of methods, statistical methods, I'd say the common tools that come up in this type of analysis are listed here. And there's vast literature on all of these things in statistics, epidemiology, econometrics, and so forth. But I did want to draw attention to a couple of emerging tools in statistical and epidemiological research for causal inference that are mentioned in the white paper fairly briefly. One is what I call this causal pathways analysis, and I'll talk briefly about two different methods for this type of analysis. And the other one is methods for quote-unquote interference. And I would characterize both of these last two emerging tools as things that are fairly cutting edge from a statistical methods standpoint, in the sense that they're very much open problems right now. So in terms of characterizing this type of causal pathway accountability, I think the ideas, conception, we think from intervention, we may want to ask the question. That's one question we may be interested in answering. Another question we may be interested in is, did this intervention causally affect health? Also a question we're probably interested in for accountability. But then there's this question of, along the lines of, did the intervention affect health through affecting air pollution? Is there evidence of this type of causal pathway in the data? The intervention reduces air pollution, let's say, and that reduction in air pollution in turn leads to some health outcome. So every arrow here is meant to be a different causal event. Now, if we're trying to think about this type of causal pathway analysis, we also have to allow for other causal pathways. It's possible that the intervention affects some other pollutant that we didn't measure. It's not the target pollutant. I mean, this is the motivation for multi-pollutant studies. The intervention was targeting PM, but really had an impact on ozone, and that's really what ended up impacting health. So we can try to quantify that type of other causal pathway. And so I'd say there are two prevailing causal inference statistical methods to answering the types of questions summarized in this little picture. The first one is often referred to as causal mediation analysis. And the basic idea with causal mediation analysis is to characterize all three of these arrows. So we have three, I just want to point out three arrows. One arrow here, one here, and then this is all one arrow here. So causal mediation analysis defines three causal effects. The causal effect of the intervention on health, which we've talked about in terms of we have an intervention and control group. It might be clear how to define that. We can also talk about the causal effect of intervention on pollution, which should be defined within this framework. But then we start talking about the causal effect of pollution on health. And I would say that the main strength of this type of approach is to identify and estimate and quantify all arrows in this causal pathway diagram. We'd be very, very happy, I think. So that's the main benefit, I'd say the main strength of causal mediation analysis. It really aims to do that. I'd say the main weakness has to do with defining this arrow here, the causal effect of pollution on health. Because remember, every time we have an arrow, we need to be thinking in the background of some hypothetical experiment that defines that causal effect. And so when we talk about this, the causal effect of the intervention on health, it's clear. We have the intervention happened here, it didn't happen here, we can compare outcomes, that's the causal effect on health. If we talk about the causal effect on pollution, similarly easy to define. If we start talking about this other causal effect, now we're talking about a hypothetical intervention that somehow intervenes directly on pollution to hold it fixed at a certain value while we start designating areas in attainment and non-attainment. So it's like we're talking about some kind of two-stage intervention where we have some regulatory decision that happens, and then we have some other way to kind of reach in, hold air pollution, even though this area was designated on attainment, what would have happened if somehow fixed the pollution to be 15? And this is a subtle point. So to be a little bit more explicit about why I, in the previous slide, described these methods as deceptively appealing, I think is what I said, is that essentially satisfying the assumptions for confounding required to identify this causal effect number 3 are going to be virtually impossible. It's going to be virtually impossible in this setting, and with the type of data we have for accountability and with the type of questions we try to answer for accountability. And we're trying to articulate this in a paper now more clearly than I just did, I'm sure. But the take-home message is that I personally don't see a lot of, as appealing as this is, I don't see a lot of potential for this type of method moving forward with accountability assessment. But that's not to say all isn't lost in terms of this causal pathway analysis. There's another method called principal stratification, which is slightly different. I would still characterize this as a causal pathways analysis to some extent. But this type of approach defines two causal effects: the causal effect of the intervention on health and the causal effect of the intervention on pollution. And as we've talked about, both of those should be at least straightforward to define. And the goal then is to determine the extent to which causal effect number one coincides with causal effect number two. So we would produce evidence along the lines of the causal effect of this regulatory decision on health was greatest in the areas where we saw the greatest reduction in air pollution. So technically speaking, this is actually not the same causal pathways analysis as depicted here. I would argue that it's still useful for informing policy decisions and analyzing and performing accountability assessments. So the main strength, I would say, is that we only define causal effects that are based on the actual intervention we're trying to study. We don't have to do any of this awkward thinking about designating an area as non-attainment, but somehow intervening to put its air pollution back up to what it would have been had it been an attainment. The main weakness is we don't actually characterize this entire picture, which would be really nice if we could do it. So I would say that this was still useful for informing policy decisions if we knew that areas experienced the greatest causal effect on pollution were also experiencing the greatest causal effect on health. I think that would still be valuable, but it's not exactly the same. And then I'll just say a couple of words about interference. What I mean by interference is a fairly subtle idea, but basically the basic idea is we say two areas interfere with one another if intervening to impact air pollution in one area ends up impacting air pollution in the other area. So we know this happens in air pollution because of the transport issues and spatial correlation and things like this. And virtually every method out there for doing this type of causal inference assumes no interference, which is clearly not the case for air pollution. And so there are basically two avenues of research in trying to make causal inference in the presence of interference. One, develop the models for interference. If we could somehow model how intervening to affect air pollution in area A spills over into other areas, we could incorporate that into our analysis. So there are folks doing work like that. And then another thing to keep in mind is, at least as far as I can tell, at times air pollution is implicit in the regulatory decisions. So the example that I have here is that, let's say the EPA knows, let's say the EPA is designating areas for non-attainment. They know that air pollution from area A is just spilling over into area B, and so the EPA knows these areas are interfering with each other on some level and then factors that into their regulatory decision. So that doesn't rely on any particular model for interference, but it's something to keep in mind, and I think it speaks to things that came up earlier about more data on the actual regulatory policies as they're being